Welcome, and thank you for settling in with us tonight. Find a comfortable position. Allow your body to sink gently into wherever you are resting, and let your breathing slow to its own natural, unhurried rhythm. Tonight, we are going to take a long and peaceful journey beyond our own solar system, drifting quietly through the vast, dark reaches of the galaxy, past stars that have never known a human eye, and toward worlds so strange and so beautiful that they seem drawn from the quietest corners of a dream. We will let each soft and distant fact wash gently over you like a slow, warm tide. For most of human history, we looked up at the night sky and wondered whether the stars held worlds of their own. We could not know. The distances were too vast, the instruments too simple, and the universe too quiet to offer any easy answers. But in the final years of the 20th century, something changed. Astronomers discovered, for the first time with certainty, that other stars, much like our own sun, were accompanied by planets. Worlds, circling in the dark, present all along, simply waiting to be found. These planets are called exoplanets. The word comes from the Greek prefix meaning outside our solar system, outside the familiar, outside everything we had ever known a world to be. Today, we have confirmed the existence of more than 5,500 of them. And with each new discovery, the universe becomes a little stranger, a little more wondrous, and, somehow, a little more peaceful. The first exoplanet ever confirmed to orbit a sun-like star was discovered in 1995 by two Swiss astronomers, Michel Mayor and Didier Queloz, working quietly at an observatory in the mountains of southern France. The planet they found was unlike anything astronomers had expected. It orbited its star not over the course of months or years, as Earth orbits our Sun, but in just 4 days. It was so close to its star that its surface temperature reached more than 1,000 degrees Celsius, and its skies glowed with a deep, permanent amber light. It was a world of extraordinary heat. A world with no seasons, no mornings, no gentle turn from night into day. Simply a vast, silent sphere of superheated gas, drifting endlessly in the warmth of its star. We called it 51 Pegasi b, and with its discovery, the universe became, for the first time, undeniably full. Beyond even that first discovered world lies a planet that, in a quieter universe, might belong to poetry rather than science. HD 189733b is a deep, cobalt blue, a color so rich and so still that astronomers initially mistook it for something ordinary. A world, perhaps, with liquid water, a world, perhaps, not so different from our own. But the color of HD 189733b does not come from oceans. It comes from glass. In its upper atmosphere, silicate particles, the same material from which glass is made, condense in the extreme heat and are swept sideways by winds that move at over 5,000 kilometers per hour. Faster than any storm that has ever touched the surface of the Earth. Faster than any storm that has ever touched the surface of the Earth. Tiny, sharp, sideways fragments of glass, falling through a blue sky on a world that no living thing has ever seen. Allow that image to settle over you for a moment. A blue planet, raining glass, in silence, billions of kilometers from here. And you, resting gently, breathing slowly, held safely in the quiet dark of your own small corner of this same extraordinary universe. An exoplanet is simply any planet that orbits a star other than our own Sun. And as of the most recent data compiled by NASA's Exoplanet Archive, astronomers have confirmed more than 5,500 individual exoplanets, with thousands more candidates still awaiting the careful verification that transforms a promising signal into an official discovery. These planets come in an astonishing variety of sizes, from tiny rocky worlds smaller than our own Earth to vast, billowing gas giants so large that they blur the boundary between planet and failed star. They orbit stars of every conceivable type, yellow stars like our Sun, cool red dwarfs, blazing blue giants, and even the dense, collapsed remnants of stars that once exploded in spectacular fashion. The word exoplanet itself is a quiet contraction of the phrase extrasolar planet, and it entered widespread scientific use only in the 1990s, when the first confirmed detections finally gave the concept a concrete, measurable reality. It is a word that carries within it the full weight of humanity's oldest question: are we alone, or is the universe filled with worlds? The very first exoplanet to be confirmed orbiting a Sun-like star was called 51 Pegasi b, and it was discovered in the year 1995 by Swiss astronomers Michel Mayor and Didier Queloz. A discovery so significant that it would eventually earn them a share of the Nobel Prize in Physics in 2019. What made the discovery so striking was not just that the planet existed, but what kind of planet it turned out to be: a gas giant roughly half the mass of Jupiter, orbiting breathtakingly close to its parent star, completing one full orbit in just over 4 Earth days. At that distance, the temperatures on such a world would be staggering, somewhere in the range of 1,000 degrees Celsius on the sunlit side, making it entirely unlike anything in our own solar system and forcing astronomers to dramatically revise their models of how planetary systems form and evolve. The detection was made using a technique called the radial velocity method, which looks for tiny wobbles in a star's movement caused by the gravitational tug of an orbiting planet. A method so elegant in its indirectness that it feels almost like detecting a dancer by watching the way the music bends. That single discovery opened a door that, once opened, could never again be closed. NASA's Kepler Space Telescope, launched in March of 2009 and named in honor of the 17th century German astronomer Johannes Kepler, was specifically designed to search for exoplanets by staring continuously at a single patch of sky containing roughly 150,000 stars. During its 9-year operational life, Kepler discovered more than 2,700 confirmed exoplanets, fundamentally transforming our understanding of how common planets are throughout the galaxy, and hinting strongly that virtually every star in the Milky Way hosts at least one world of its own. The telescope used what is called the transit method, watching for the tiny, regular dimming of a star's light that occurs when a planet passes in front of it. A dimming so subtle that it might represent a change of only 1 part in 10,000 in the star's overall brightness. Kepler's data revealed that small, rocky planets appear to be extraordinarily abundant across the galaxy, far more so than the large gas giants that had dominated the early years of exoplanet discovery simply because they were the easiest to find. When the telescope finally ran out of fuel and was retired in October 2018, it left behind a scientific legacy so rich that researchers are still mining its data archives today, finding new worlds hidden in its vast, patient recordings of starlight. Among the most surprising categories of exoplanet to emerge from the early years of discovery are the so-called hot Jupiters, massive gas giants that orbit extraordinarily close to their parent stars, completing full orbits in just a few Earth days and basking in temperatures that can exceed 2,000 degrees Celsius on their sunlit faces. These worlds have no counterpart in our own solar system, where Jupiter itself orbits the Sun at a comfortable distance of nearly 800 million kilometers and takes almost 12 Earth years to complete a single revolution. The existence of hot Jupiters forced a complete rethinking of planetary formation theory, because the leading scientific understanding was that gas giants could only form in the cold outer regions of a solar system, far from their star's heat, and must therefore have migrated inward over millions of years after their formation. Some hot Jupiters are so puffed up by the intense stellar radiation they receive that their density is less than that of styrofoam, enormous worlds with masses many times that of Jupiter but radii so swollen that they barely qualify as dense objects by planetary standards. Despite their strangeness, hot Jupiters have taught astronomers more about planetary physics than perhaps any other category of world, precisely because their extremity makes the underlying processes so visible and measurable. Super-Earths are one of the most common types of exoplanet discovered so far, and yet they represent a category of world that does not exist anywhere in our own solar system. Planets with masses somewhere between 1 and 10 times the mass of Earth. Larger and heavier than our world, but still fundamentally rocky in character rather than being composed primarily of swirling gas. The name can be a little misleading, because a super-Earth is not necessarily an Earth-like world in any comfortable, familiar sense. Many of these planets orbit very close to their stars and may have thick, crushing atmospheres, or surfaces completely covered in global oceans, or interiors of exotic high-pressure minerals that behave in ways nothing on Earth quite prepares us for. Some super-Earths sit in what astronomers call the habitable zone of their star, the orbital distance at which liquid water could theoretically exist on a planetary surface, which makes them among the most intensely studied objects in the search for potentially life. Bearing worlds. The planet Kepler 452b, discovered in 2015, is one of the most celebrated super-Earths, orbiting a Sun-like star at nearly the same distance that Earth orbits our own Sun, and receiving a similar amount of stellar energy, though its precise nature remains subject to ongoing study. Super-Earths remind us, gently and persistently, that the universe has no obligation to limit itself to the categories of world our own solar system happened to produce. Among the most quietly haunting categories of world in the universe are rogue planets. Planets that do not orbit any star at all, but instead drift freely through the cold, dark interstellar space between stellar systems, unattached, untethered, traveling through the galaxy alone in the long, slow darkness. These worlds are believed to form in one of two ways. Either they are born as part of a normal planetary system, and are eventually flung outward by gravitational interactions with other planets. Expelled like stones from a sling into the deep void, or they condense directly from clouds of gas and dust in space in a manner more similar to the way stars form than the way planets typically do. Estimates suggest that rogue planets may actually outnumber stars in the Milky Way galaxy, making them extraordinarily common even as they remain extraordinarily difficult to detect, since they emit no light of their own and have no star to reflect. Some scientists have proposed that rogue planets with thick hydrogen atmospheres or sufficient internal radioactive heat could theoretically maintain liquid water somewhere beneath their surfaces. Even in the total absence of a star, which opens quiet and fascinating questions about what forms life might take on such a world. The James Webb Space Telescope has already identified numerous rogue planet candidates in nearby star-forming regions. Some of them apparently drifting in pairs, locked in a slow gravitational dance with one another through the darkness. The habitable zone around a star, sometimes called the Goldilocks zone in a nod to the fairy tale, is the range of orbital distances within which a planet with the right atmospheric conditions could maintain liquid water on its surface. A condition that Earth's biology has made synonymous, perhaps somewhat provincially, with the possibility of life. The precise boundaries of the habitable zone are not fixed but depend on the type and luminosity of the host star, as well as the composition of the planet's atmosphere, its albedo, and a host of other factors that make the calculation far more nuanced than a simple circle drawn around a star on a diagram. A planet orbiting a dim red dwarf star, for example, would need to orbit much closer in to receive enough warmth to maintain liquid water, while a planet around a blazing blue giant would need to sit at a vast distance to avoid being roasted. As of early 2024, astronomers had identified dozens of confirmed exoplanets sitting within the habitable zones of their stars, with hundreds more candidates awaiting verification. The concept of the habitable zone, though enormously useful as a first filter in the search for potentially life-bearing worlds, is now understood to be only a starting point because moons of gas giants, worlds warmed by tidal forces rather than starlight, and planets with entirely different biochemistries might exist in conditions we would not at first think to look. The TRAPPIST-1 system, located approximately 40 light-years from Earth in the constellation Aquarius, contains 7 confirmed planets, all of them roughly Earth-sized and rocky, and all of them orbiting a single small, cool red dwarf star, making it the largest collection of Earth-sized worlds ever found around a single star, and one of the most studied planetary systems in all of astronomy. The system was first detected using a small Belgian telescope called TRAPPIST, an acronym that stands for Transiting Planets and Planetesimal Small Telescope. And the discovery was subsequently confirmed and expanded using data from the Spitzer Space Telescope and the Hubble Space Telescope. Of the 7 planets, 3, named TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g, orbit within the star's habitable zone, where conditions might theoretically allow for liquid water, and the James Webb Space Telescope has been deployed to study their atmospheres in unprecedented detail. Because the planets orbit so close together and so close to their dim star, the gravitational interactions between them cause subtle variations in their transit timings that allow astronomers to precisely measure their masses and densities. revealing that several of the worlds have densities consistent with rocky compositions, possibly with significant amounts of water. The TRAPPIST-1 system is, in many ways, the most tantalizing example humanity has yet found of a place in the universe that raises the soft, persistent question of whether someone, or something, might be looking back. HD 189733b is a deep blue exoplanet orbiting its star at a distance of just over 3 million kilometers, about 30 times closer than Mercury is to our own Sun. And beneath its striking cobalt blue appearance lies an atmosphere of almost unimaginable violence and alien beauty. The blue color of this world is not caused by oceans of water as it is on Earth, but rather by the presence of tiny silicate particles suspended throughout its atmosphere. Particles formed when the extraordinarily high temperatures vaporize rock and silicon, which then condense at higher altitudes into a kind of perpetual glassy haze. Wind speeds on HD 189733b are estimated to reach up to 8,800 kilometers per hour, roughly 20 times the speed of sound. And these winds carry the silicate particles horizontally at such velocity that they effectively rain sideways at speeds that would pulverize almost any structure we might imagine. The planet is tidally locked to its star, meaning one side faces perpetual blazing day and the other perpetual night, while the boundary between these two hemispheres is a region of fierce, churning atmospheric turbulence. Despite its beauty from a distance, that deep, rich blue visible even in the data collected by the Hubble Space Telescope, HD 189733b is a reminder that color alone tells us nothing about the nature of a world. The oldest confirmed exoplanet discovered so far is a world called PSR B 1620-26b, sometimes given the evocative nickname Methuselah after the long-lived biblical patriarch. And it is estimated to be approximately 12.7 billion years old, more than 2.5 times the age of the Earth and nearly as old as the universe itself, which formed roughly 13.8 billion years ago. This extraordinary planet orbits not one star but two, a pulsar and a white dwarf, both of which are themselves the remnants of stars that lived and died long before our Sun had even begun to form from its cloud of gas and dust. The planet is located in the globular cluster M4, a dense, ancient congregation of stars approximately 5,600 light-years from Earth in the constellation Scorpius. Its existence raises profound and gentle questions about the deep history of planetary formation in the universe, suggesting that rocky and gaseous worlds may have been forming around stars almost since the earliest chapters of cosmic time. To contemplate Methuselah is to be reminded that the universe is incomprehensibly old, and that the story of planets, of solid, orbiting worlds, is very nearly as old as the story of stars themselves. White dwarfs are the dense, cooling remnants of stars like our Sun that have exhausted their nuclear fuel and shed their outer layers. And for many years astronomers assumed that the violent process by which a star dies would destroy any planets that might have been orbiting it. However, recent observations have revealed that planetary systems can indeed survive stellar death, and that some white dwarfs are orbited by the remnants of their original planetary systems, shattered asteroids, rocky debris disks, and in some cases planets that managed to survive the transformation of their parent star. The white dwarf WD 1856 + 534, discovered in 2020, hosts a confirmed planet-sized object approximately 6 times the mass of Jupiter that somehow survived the death of its star and migrated inward to its current close orbit, a journey whose mechanics are not yet fully understood. The atmospheres of many white dwarfs show contamination by metals such as calcium, magnesium, and iron, elements that have no business being in a white dwarf's atmosphere, where they should sink rapidly, suggesting that the white dwarf is actively accreting or consuming the rocky debris of destroyed planetary bodies. These observations paint a quiet picture of planetary systems as resilient, persistent structures that can endure across billions of years and through the death of the stars that gave them birth. 55 Cancri e is a super-Earth roughly 8 times the mass of our own planet, orbiting its sun-like star at an extraordinarily close distance of only about 2 million kilometers, so close that a full year on this world lasts approximately 18 Earth hours. And surface temperatures on the sunlit side are estimated to reach around 2000 degrees Celsius. What makes 55 Cancri e particularly remarkable is its proposed interior composition. Early scientific analyses suggested that, given the carbon-rich nature of its host star and the extreme pressures deep within the planet's mantle, much of its interior could potentially be composed of crystalline carbon in the form of diamond, an idea that led to widespread coverage under the simple, evocative description of a diamond planet. More recent observations from the James Webb Space Telescope have detected evidence of a possible thin atmosphere containing carbon dioxide and carbon monoxide, suggesting the planet is more complex than its early characterizations allowed. The surface of 55 Cancri e is likely molten or semi-molten, with rivers and oceans of liquid rock flowing across its perpetually roasted face, making it one of the most extreme rocky worlds yet observed in such detail. It sits in the constellation Cancer, approximately 41 light-years from Earth, close enough that its properties can be studied with considerable precision using current instruments. WASP-76b is a hot Jupiter located about 640 light-years from Earth in the constellation Pisces, and it has become one of the most discussed exoplanets in recent memory because of an observation that stretches the imagination in the most literal way possible. On the night side of this planet, the atmospheric conditions appear to support a kind of iron rainfall, where vaporized iron from the day side is carried around by fierce winds, cools at higher altitudes on the colder night side, and condenses into droplets that fall downward through the atmosphere. The day side of WASP-76b reaches temperatures of around 2,400 degrees Celsius, hot enough to vaporize iron, which on Earth requires temperatures of around 2,800 degrees in laboratory conditions, while the night side is somewhat cooler, allowing that vapor to transition back into a liquid or solid state. The detection was made using the espresso spectrograph on the Very Large Telescope in Chile, which measured the absorption signature of iron vapor at the boundary between the planet's day and night sides. WASP-76b is tidally locked to its star, meaning the same hemisphere always faces the blazing sun while the other languishes in permanent darkness, creating a permanent and extreme temperature gradient across the planet's face. The image of iron rain falling softly but lethally through an alien night sky is one that has lodged itself firmly in the collective imagination of modern astronomy. Among the many types of exoplanet that have captured scientific imagination are the so-called water worlds, planets that appear to contain such enormous quantities of water that their entire surfaces would be submerged under global oceans potentially hundreds or even thousands of kilometers deep. Oceans so deep that the water at the bottom would not be liquid in the conventional sense but compressed into exotic high-pressure phases of ice that can exist at temperatures well above the normal melting point because of the immense weight pressing down upon them. The exoplanet Kepler 22b, located approximately 620 light-years from Earth and orbiting comfortably within its star's habitable zone, has been proposed as a candidate water world based on its size, mass, and density estimates, though definitive characterization of its surface awaits better instruments. GJ 1214b, a super-Earth approximately 40 light-years away, is another strong candidate for a water-rich world, with observations suggesting it is surrounded by a thick, steam-filled atmosphere that would be consistent with a global ocean beneath. These worlds are fascinating not only for their physical strangeness but for the questions they raise about life. Earth's deep ocean ecosystems demonstrate that life can thrive in perpetual darkness, under crushing pressure, far from sunlight, sustained entirely by chemical energy rather than photosynthesis. A world of endless ocean, stretching down into unfathomable darkness, suggests a kind of life so different from our own that it asks us to expand every definition we have ever used. Among the diverse population of exoplanets catalogued by astronomers, some worlds stand out for their remarkable physical density. And near the top of that list sits a planet called Kepler 131b, as well as a category of worlds sometimes described as ultra-dense super-Earths whose interiors are believed to be composed predominantly of iron, with proportionally thin rocky mantles over what amounts to an almost entirely metallic core. For comparison, Mercury in our own solar system is the densest planet, with a density about 5.5 times that of water, a value driven by its unusually large iron core relative to its total size, and some exoplanets appear to have similar or even more extreme compositions. The planet 55 Cancri E, discussed earlier, has a density considerably higher than Earth's, while other candidates have densities suggesting they are almost entirely made of iron compressed by intense gravity into extraordinarily compact forms. These worlds raise fascinating questions about the geological and volcanic histories that such planets would have, since an iron-rich world with minimal silicate mantle might behave very differently from Earth in terms of plate tectonics, volcanism, and the cycling of elements through its interior. The existence of such worlds reminds us that the solar system we grew up studying is merely one data point in an almost infinitely varied collection of planetary outcomes. Our own solar system has a single star at its center, but a significant fraction of the stars in the Milky Way are actually part of binary or multiple star systems. Pairs or groups of stars bound together by gravity and orbiting their common center of mass, and the question of whether planets can form and survive in such complex gravitational environments has fascinated astronomers for decades. The answer, it turns out, is a resounding yes. NASA's Kepler telescope discovered numerous so-called circumbinary planets, worlds that orbit both stars of a binary pair simultaneously, traveling in large loops around the shared center of the system the way a coin might orbit the inside of a bowl. The most famous of these is Kepler 16b, the first unambiguous circumbinary planet to be confirmed, which orbits two stars, one about 2/3 the mass of our Sun and one about 1/5 of its mass, at a distance of about 1 astronomical unit, placing it near the outer edge of the system's habitable zone. Observers on Kepler 16b, if there were any, would sometimes witness a single sunrise and at other times a double sunrise, depending on the relative positions of its two suns at any given moment, a sight that once seemed purely the domain of science fiction. The existence of stable, potentially habitable planets around binary stars more than doubles the number of stellar environments that astronomers must consider when thinking about where life might find a foothold in the cosmos. A tidally locked planet is one whose rotation has been slowed by the gravitational pull of its parent star to the point where the planet's day and its year are exactly the same length, meaning one hemisphere permanently faces the star in unceasing day while the other faces perpetual darkness. A condition that Earth's own moon demonstrates closer to home, with one face always turned toward us and the other forever hidden. Many of the most promising potentially habitable exoplanets, particularly those orbiting small, dim red dwarf stars, are expected to be tidally locked, because the habitable zones of such stars are so close in that tidal forces would have acted strongly enough over geological timescales to synchronize the planet's rotation. For a long time, scientists worried that a tidally locked planet would be inhospitable to life, with one side blasted to lethally high temperatures and the other frozen solid. But sophisticated atmospheric modeling has since suggested that a sufficiently thick atmosphere could redistribute heat efficiently around the planet, moderating temperatures and potentially allowing a wide habitable belt along the twilight boundary between day and night. The atmospheric dynamics of such a world would be extraordinary vast circulation cells driven by the permanent temperature gradient between hemispheres, creating permanent storm systems at specific latitudes and a complex web of winds unlike anything in Earth's weather system. Standing at the terminator line of a tidally locked planet where day ends and night begins, in a line as sharp as a drawn curtain would mean standing in a perpetual amber sunset, the star always hanging on the horizon, the sky behind you black and star-filled, the sky before you blazing with light. NASA's Transiting Exoplanet Survey satellite, known by the elegant abbreviation TESS, was launched in April 2018 as the successor and complement to the Kepler Space Telescope, designed to survey a far larger portion of the sky, and to focus in particular on the nearest and brightest stars, the ones close enough that follow-up observations with ground-based and space-based telescopes would be most feasible and productive. In the first several years of its operation, TESS identified more than 7,000 exoplanet candidates and confirmed hundreds of new worlds, including rocky planets, sub-Neptunes, and the occasional hot Jupiter, building a catalogue of nearby planetary systems that will keep astronomers busy for decades. Unlike Kepler, which stared at a fixed patch of the sky for years at a time, TESS surveys the entire sky by dividing it into sectors and observing each for approximately 27 days before moving on, returning to revisit sectors in subsequent years. One of TESS's most celebrated early discoveries was the system TOI 700, which includes a rocky planet called TOI 700d sitting within the habitable zone of a small red dwarf star approximately 100 light-years away, a world whose potential and properties continue to be studied with increasing precision. TESS is expected to continue operating for many years, and its catalogue of nearby planetary systems will serve as the primary target list for the James Webb Space Telescope's atmospheric investigations and for future missions designed to image Earth-like exoplanets directly. One of the most active and exciting frontiers in exoplanet science is the study of planetary atmospheres, the thin or thick envelopes of gas that surround a world and mediate between the raw energy of a star and the surface conditions below. Because it is in these atmospheric layers that the most direct chemical signatures of a planet's nature, and potentially its biology, might be found. When an exoplanet passes in front of its star during a transit, a small fraction of the star's light filters through the planet's atmosphere before reaching our telescopes, and by carefully analyzing the wavelengths of that filtered light, astronomers can identify which molecules are present in the atmosphere based on their characteristic absorption signatures, a technique called transmission spectroscopy. Using this method, scientists have already detected water vapor, carbon dioxide, carbon monoxide, methane, sodium, potassium, and even signs of complex organic molecules in the atmospheres of various exoplanets, building a growing catalog of atmospheric chemistry that spans a remarkable range of compositions. The James Webb Space Telescope, with its unprecedented infrared sensitivity, has pushed this capability to extraordinary new levels, detecting carbon dioxide in the atmosphere of the hot gas giant WASP-39b with a clarity that was simply impossible before its launch. Perhaps most tantalizing of all is the ongoing search for what scientists call biosignatures in exoplanet atmospheres, gases like oxygen, ozone, or a simultaneous presence of methane and carbon dioxide that would be chemically unstable without a continuous biological source, a kind of chemical fingerprint that life, and almost nothing else, would leave upon the air of a distant world. The largest exoplanets yet discovered are members of a category sometimes called superjupiters or hot Jupiters, and some of them have radii so inflated by the intense stellar radiation they receive that they are nearly 2 or even 3 times the physical size of Jupiter, the largest planet in our own solar system, despite having similar or even lesser masses, resulting in densities approaching those of expanded foam. Among the record holders is ROX's 42Bb, a world with an estimated radius approximately 2.5 times that of Jupiter, orbiting a young star in the constellation Ophiuchus, though distinguishing the boundary between a very large planet and a very small brown dwarf becomes genuinely blurry at these extremes. HAT P32b is another enormous exoplanet, with a radius nearly twice that of Jupiter, so puffed up that its atmosphere extends thousands of kilometers above its notional surface. These ultra-puffy worlds exist because intense stellar irradiation heats the upper atmosphere so dramatically that it expands far beyond what an isolated planet would achieve through its own internal heat alone, a process called thermal inflation that continues to be modeled and refined. The sheer size of these worlds is humbling to contemplate. Spheres of swirling gas many times larger than the largest planet humanity has ever known, drifting in the darkness around their stars with a slow, enormous majesty. At the other end of the size spectrum, astronomers have discovered exoplanets that are comparable in size to Earth's moon or even smaller, tiny, rocky worlds whose detection represents an extraordinary technical achievement, since finding a small planet orbiting a distant star requires measuring changes in starlight that are almost vanishingly subtle. Kepler 37b holds the distinction of being one of the smallest exoplanets confirmed to date, with a radius only slightly larger than that of the Moon and orbiting very close to its star in a blazing, airless environment not unlike a superheated version of Mercury. The detection of such small worlds is pushing the boundaries of what current instrumentation can achieve, and future telescopes are expected to find progressively smaller planets around progressively more distant stars as sensitivity improves. The existence of moon-sized exoplanets suggests that the processes of planet formation can produce objects across an enormous range of sizes, from these tiny rocky pebbles orbiting in blasting heat to the enormous gas giants that dwarf every planet in our solar system. Small as they are, these worlds carry the same fundamental dignity as any planet. They are formed from the same cosmic materials, shaped by the same gravitational forces, and orbit their stars in the same patient, unending dance that has been underway since long before any eye existed to observe it. Just as planets in our solar system are orbited by moons, it is theoretically expected, and increasingly supported by observational hints, that many exoplanets should also host moons of their own, objects called exomoons, whose detection would add an entirely new layer of complexity and richness to our understanding of planetary systems beyond our own. Detecting an exomoon is significantly harder than detecting an exoplanet, because a moon produces an even tinier perturbation in the light curves and timing signatures that astronomers analyze, requiring extraordinary precision and patience to disentangle from noise. The most compelling exomoon candidate discovered so far is orbiting a gas giant called Kepler 1625b, a moon estimated to be roughly the size of Neptune, which would make it a moon of extraordinary proportions compared to anything in our own solar system, though the confirmation remains subject to ongoing scientific debate. Another candidate, Kepler 1708bi, was identified in 2022, and while neither candidate has yet achieved the full certainty of confirmed status, the scientific community widely expects that the first confirmed exomoon discovery is a matter of when rather than whether. The existence of large, complex moons around exoplanets opens the imagination further still, because a moon orbiting a gas giant in a habitable zone could itself be a world with stable temperatures, liquid water, and all the conditions that Earth's particular arrangement has produced. Before 51 Pegasi b announced itself as the first planet found around a Sun-like star in 1995, the very first confirmed exoplanets were discovered orbiting an entirely different and far more dramatic type of stellar remnant, a pulsar, which is the collapsed, rapidly spinning core of a massive star that exploded in a supernova, now emitting beams of radio waves so precisely timed that they function like the most accurate clocks in the known universe. In 1992, astronomer Alexander Wolszczyn detected planets around the pulsar PSR 1257+12 by noticing tiny, regular variations in the arrival times of the pulsar's radio pulses, variations caused by the gravitational influence of orbiting bodies tugging the pulsar slightly toward and away from Earth. 3 planets were ultimately confirmed around this pulsar, 2 of which are roughly 4 times the mass of Earth and 1 of which is smaller than the Moon, and they orbit their pulsar host at distances comparable to Mercury's distance from our Sun, bathed in intense radiation from the pulsar itself. How these planets came to exist remains an open question. They may be the survivors of the original planetary system that survived the supernova, though transformed beyond recognition, or they may have formed from the disk of debris left behind by the explosion itself. Pulsar planets are not considered promising candidates for life as we know it, because pulsar radiation is extraordinarily energetic and hostile, but their existence alone demonstrates that planets can form and persist in the most extreme stellar environments imaginable. The title of most Earth-like exoplanet is contested and frequently updated as new discoveries emerge, but among the strongest current candidates is Kepler 452b, a world sometimes referred to informally as Earth's older bigger cousin. It is approximately 60% larger than Earth in diameter, orbits a Sun-like star in the habitable zone, and completes one orbit every 385 days, a year almost identical in length to Earth's own. The host star of Kepler 452b is approximately 1.5 billion years older than our Sun, which means that if the planet has ever harbored life, that life has had considerably more time than Earth's own biosphere to develop and evolve. a thought that is both quiet and enormous. However, the planet's larger size means its surface gravity is estimated to be roughly double that of Earth's, and its potentially thicker atmosphere and enhanced volcanic activity might produce conditions quite different from our own worlds, despite the surface similarities in orbital parameters. Kepler 452b is approximately 1400 light-years away, which means the light we use to study it left the planet around the year 620, when the Earth was a very different place. Whether it has an atmosphere, liquid water, or any of the other conditions associated with habitability remains unknown, but it stands as a compelling reminder that the universe has had more than enough time and space to produce many worlds whose broad parameters resemble ours. A lava world is a rocky planet whose surface temperature is so extreme, typically because it orbits very close to its star, that its entire surface is covered in a global ocean of molten magma. A sea of liquid rock kilometers deep, glowing with its own internal light in shades of deep red and orange and occasionally punctuated by volcanic plumes that erupt upward through the liquid surface before falling back as molten rain. Kepler 10b, discovered in 2011 and the first rocky exoplanet confirmed by the Kepler mission, is one of the most well-characterized lava worlds. It completes an orbit around its star in just 20 hours. Sits at a distance of only about 2 million kilometers from its sun, and has dayside temperatures estimated at around 1,400 degrees Celsius, hot enough to keep most silicate rocks in a perpetually liquid state. Kourou T7b, another lava world candidate, orbits so close to its star that the tidally locked dayside is thought to experience rock vapor weather, where the extreme heat vaporizes silicate minerals into a thin gaseous atmosphere that condenses and rains back down as pebbles on the cooler parts of the surface. These worlds are genuinely alien in every sense, and yet they are not so unlike the young Earth of 4 billion years ago, when our own planet's surface was largely molten and the cooling of that primordial magma ocean was among the earliest geological events in Earth's history. A lava world seen from space would glow with its own dim light on the night side, a faint red ember drifting through the dark. The transit method is the most productive technique ever devised for discovering exoplanets, and it works by monitoring the brightness of a star over time and looking for the tiny, periodic dips that occur when an orbiting planet passes in front of the stellar disk as seen from Earth, in the same way a small insect walking across a lamp would cause an almost imperceptible dimming of the light. The amount of dimming depends on the ratio of the planet's cross-sectional area to the star's cross-sectional area, which means that a Jupiter-sized planet transiting a Sun-like star would produce a dip of roughly 1%. While an Earth-sized planet produces a far more challenging dip of only about 1/100th of 1%. The transit method is beautifully systematic. It not only reveals the planet's size but also, combined with the timing of successive transits, provides its orbital period, and when combined with radial velocity measurements of the star's wobble, allows astronomers to calculate the planet's density and make inferences about its composition. One of the inherent limitations of the transit method is that it can only detect planets whose orbits happen to be aligned such that the planet passes between its star and Earth, a geometric coincidence that, for Earth-like planets around Sun-like stars, occurs for only about 0.5% of all systems, meaning that for every Earth twin we detect by transits, hundreds more are likely orbiting stars at other angles, invisible to this particular technique. Despite this limitation, transit photometry has delivered the majority of the world's confirmed exoplanet catalog and remains the foundation upon which the field was built. The radial velocity method, also called Doppler spectroscopy, detects exoplanets by measuring the subtle wobble that a planet induces in its parent star through gravitational attraction. Because as a planet orbits, it does not merely circle a stationary star, but rather both the planet and the star orbit their common center of mass, causing the star to trace a tiny ellipse in space and to move alternately toward and away from Earth with a regular periodicity. This motion produces a measurable Doppler shift in the star's light, compressing wavelengths slightly as the star approaches and stretching them as it recedes, in the same way a siren rises in pitch as an ambulance approaches and falls as it passes. The method was pioneered in the detection of 51 Pegasi b in 1995 and has since been responsible for confirming hundreds of exoplanets, particularly massive ones whose gravitational tugs are large enough to produce detectable stellar wobbles. For a hot Jupiter, the wobble it induces in a Sun-like star might amount to tens or even hundreds of meters per second, large enough for relatively modest instruments to detect. But an Earth-mass planet in an Earth-like orbit would induce a wobble of only about 9 centimeters per second, requiring extraordinarily precise spectrographs to measure. Modern instruments like HARPS and ESPRESSO on European Southern Observatory telescopes are achieving radial velocity precision approaching 1 meter per second, pushing the boundaries of what smaller, potentially habitable worlds can be detected with this elegant and indirect method. While most exoplanet detection relies on indirect methods, measuring a star's wobble or the dimming of its light, astronomers have also managed, in a number of extraordinary cases, to directly image exoplanets as distinct points or smears of light separate from their parent stars. A feat that requires overcoming the tremendous challenge of separating the faint glow of a planet from the overwhelming glare of its nearby star, a contrast challenge comparable to trying to see a firefly hovering beside a searchlight from a great distance. The technique has been most successful for large, young, hot gas giant planets far from their stars, because these worlds still retain some of the heat from their formation and emit significant infrared radiation of their own, making them relatively bright and helping instruments distinguish them from starlight. HR 8799, a star approximately 130 light-years away in the constellation Pegasus, hosts 4 directly imaged planets, all of them massive gas giants orbiting at considerable distances from their star, in one of the most visually compelling exoplanet system images ever captured. Beta Pictoris b is another celebrated directly imaged planet, a young gas giant caught in the act of formation around a star famous for its edge-on debris disk, allowing astronomers to study the early stages of planetary system evolution in something approaching real time. Future instruments, including space-based coronagraph missions specifically designed to block stellar light, aim to eventually image Earth-sized planets directly and analyze the light reflected from their surfaces for the chemical fingerprints of atmospheres, oceans, and perhaps biology. Sub-Neptunes, sometimes called Mini-Neptunes, are a category of exoplanet found in enormous numbers throughout the galaxy that are smaller than Neptune but larger than Earth, typically 2 to 4 times Earth's radius, and yet they have no counterpart anywhere in our own solar system, sitting in what astronomers have called the gap between our rocky terrestrial planets and our smallest gas giant, a gap that our solar system curiously never filled. These worlds may have thick gaseous envelopes composed largely of hydrogen and helium surrounding rocky or icy cores, or they may be water-rich worlds with dense steam atmospheres, and distinguishing between these possibilities requires precise measurements of both their sizes and their masses, because 2 planets identical in size can have very different densities and thus very different compositions. One of the most intriguing features of the sub-Neptune population is the so-called Radius Gap or Fulton Gap, a statistical scarcity of planets between approximately 1.5 and 2 times Earth's radius that appears prominently in the Kepler data, suggesting that some physical process, likely photoevaporation, where stellar radiation strips away a planet's atmosphere over time, is pushing planets to either side of this size range. The planet GJ1214b is perhaps the best-studied sub-Neptune, and despite extensive observation it remains genuinely ambiguous whether it is a water world, a gas-rich Mini-Neptune, or something else entirely, a reminder that even the most studied exoplanets retain deep mysteries. Sub-Neptunes are thought to be the single most common type of planet in the galaxy, which makes the absence of any such world in our own solar system a curious and not yet fully explained peculiarity of our cosmic neighborhood. The James Webb Space Telescope, launched on Christmas Day 2021 and reaching its operational configuration at the second Lagrange point of the Sun-Earth system in early 2022, represents the most powerful astronomical instrument ever built for studying the infrared universe, and among its most significant scientific contributions has been the unprecedented detail it has brought to the study of exoplanet atmospheres. Using its near-infrared camera and its mid-infrared instrument, JWST can analyze the atmospheric transmission spectra of transiting exoplanets with a sensitivity and wavelength coverage that far surpasses any previous space telescope, allowing it to detect molecular species that were previously beyond reach and to measure temperature profiles and cloud structures in alien atmospheres with remarkable precision. In its early science operations, JWST detected carbon dioxide in the atmosphere of the hot Jupiter WASP-39b with unambiguous clarity, the first unequivocal detection of carbon dioxide in an exoplanet atmosphere, and followed this with a cascade of atmospheric detections and characterizations that reshaped understanding of atmospheric chemistry across the exoplanet population. JWST is expected to make its most profound contributions through the long-term atmospheric study of the TRAPPIST-1 system planets, whose proximity and the small size of their host star make them among the most favorable targets for atmospheric characterization with current technology. In a very real sense, JWST represents the moment in human history when the study of exoplanet atmospheres matured from occasional hints and suggestions into a genuine, systematic, detailed science. The naming of exoplanets follows a systematic but somewhat unglamorous convention that reflects the scientific origins of each discovery rather than the poetic imagination that the subject might otherwise inspire. In the most common scheme, a planet is named by appending a lowercase letter to the name of its host star, beginning with the letter B for the first confirmed planet because the letter A is reserved for the star itself and proceeding through the alphabet for subsequent planets in the same system. So that a star with 3 planets would host planets B, C, and D. Stars in major catalogs carry alphanumeric designations like Kepler 452 or HD 189733 or WASP 76, reflecting the catalog or survey in which they were first recorded. While stars also commonly known by traditional names carry those names as well, so that Alpha Centauri's planetary companion is sometimes referred to as Alpha Centauri BB. Since 2015, the International Astronomical Union has run a series of public naming campaigns that have given official proper names to a selection of exoplanets, working with member countries to propose and vote on names drawn from local mythology, history, and culture, so that planets now carry names like Dimidium, Arion, Galileo, Lippershey, and hundreds of others that give these distant worlds a slightly more personal identity. The gap between a catalog number and a name is, in many ways, the gap between an object of study and a place, and the slow accumulation of proper names for exoplanets is a quiet, ongoing act of human imagination, of reaching across light years with nothing more than a word. The boundary between the largest possible planet and the smallest possible star is not a sharp line but rather a gradual, somewhat ambiguous transition zone occupied by objects called brown dwarfs, bodies too massive to be considered planets by most definitions but too small and cool to sustain the hydrogen fusion that defines a true star, instead relying briefly on deuterium fusion before slowly cooling and fading over billions of years into darkness. By the most widely used definition, an object above approximately 13 Jupiter masses that undergoes deuterium fusion during its life is classified as a brown dwarf rather than a planet, while objects below this threshold are planets regardless of how they formed, though formation history is sometimes considered as well. Some directly imaged objects orbiting stars appear to fall near this boundary, and their classification as planet or brown dwarf depends on precise mass estimates that are not always easy to obtain. Brown dwarfs themselves were first confirmed in 1995, the same year as the first exoplanet around a Sun-like star, and they fill the space between the largest gas giant planets and the smallest red dwarf stars in the astronomical census of the universe. The existence of this continuum between planet and star is a reminder that nature does not always organize itself into the clean categorical boxes that human classification systems prefer, and that some of the most interesting objects in astronomy sit quietly at the edges of our definitions, defying easy description. The 7 planets of the TRAPPIST-1 system do not simply orbit their star independently. They are locked together in a nearly perfect chain of orbital resonances, meaning that each planet's orbital period forms a precise ratio close to a small whole number with its neighbors. This arrangement, thought to have formed during the early gas disk phase of the system's history when the planets were migrating inward and settling into gravitationally stable configurations, produces a gravitational choreography of extraordinary elegance. The resonances allow astronomers to measure the planets' masses with great precision by analyzing the tiny, regular variations in their transit timings caused by the gravitational tugs they exert on one another, a technique that turns the music of their orbital dance into a measurement of their physical weight. Gliese 667c is a small red dwarf star located approximately 23 light-years from Earth, forming part of a triple-star system in the constellation Scorpius, and it hosts what may be as many as 3 planets simultaneously within its habitable zone, a density of potentially temperate worlds around a single star that remains remarkable by any measure. Gliese 667cc. The most studied of these planets is a super-Earth with at least 4 times Earth's mass, orbiting its star every 28 days in a zone where liquid water could theoretically persist on its surface. From the surface of any world in this system, the sky would contain not only the dim red primary star but 2 additional stellar companions shining in the background, a sky unlike anything that has ever been seen by any eye on Earth. Most planets in our solar system follow nearly circular orbits around the Sun, but the exoplanet HD 80606b moves in an extraordinarily elongated ellipse, with an eccentricity of about 0.93, one of the most extreme orbital shapes of any confirmed exoplanet. At its closest approach, the planet swings to within about 4 million kilometers of its star, where the temperature shoots up by hundreds of degrees within just a few hours. At its farthest point, it drifts out to about 85 million kilometers, a range of distances that subjects this world to wild swings in stellar energy with each orbit. This eccentric history is thought to reflect a past of gravitational interactions with other planetary bodies that gradually sculpted its orbit into its current dramatic elongated form. The Kepler-90 system, located approximately 2,500 light-years from Earth, hosts 8 confirmed planets orbiting a Sun-like star, tying our own solar system for the most planets known around a single star at the time of its full discovery. A neural network developed by Google, trained on Kepler's light curve data, identified the 8th planet in 2017, demonstrating for the first time that artificial intelligence could find exoplanets that had been overlooked by conventional analysis methods. The 8 planets of Kepler-90 are arranged in a general pattern of smaller inner worlds and larger outer worlds broadly similar to our own solar system's architecture, suggesting that this kind of arrangement may be a recurring outcome of the planet formation process. Coconuts 2b, discovered in 2021, holds the distinction of being one of the coldest and most distant exoplanets from its host star ever directly imaged, orbiting at approximately 6,000 astronomical units, 6,000 times the Earth-Sun distance, with an estimated atmospheric temperature of only about 60 degrees above absolute zero. At that distance, the planet takes more than 1 million Earth years to complete a single orbit of its star, a year of such incomprehensible length that our entire recorded human history would represent only the tiniest fraction of a single one of this planet's years. Its detection in infrared light, glowing faintly with residual heat from its formation, illustrates how even the most distant and dim planetary companions can reveal themselves to patient instruments. On Earth, clouds are made of water droplets and ice crystals, but on exoplanets with different atmospheric chemistries, the cloud particles can be composed of iron droplets, magnesium silicate dust, potassium chloride crystals, zinc sulfide particles, or even more exotic materials that have no counterpart in any atmosphere in our solar system. The hot Jupiter Kepler 7b is one of the most extensively studied cloudy exoplanets, with reflective silicate clouds mapped preferentially to its western dayside hemisphere in a distribution that atmospheric models have worked hard to reproduce. These exotic cloud compositions are not hypothetical or speculative. They are derived from direct analysis of the wavelengths of starlight that each planet's atmosphere absorbs and scatters, a kind of chemical fingerprinting conducted across light-years of intervening space. The 55 Cancri system, located approximately 41 light-years from Earth in the constellation Cancer and faintly visible to the naked eye from a dark sky, hosts 5 confirmed planets, one of which, 55 Cancri e, is a lava-covered super-Earth completing an orbit every 18 hours, while the outermost, 55 Cancri d, is a gas giant 4 times Jupiter's mass orbiting at roughly the distance of Jupiter from our Sun. The architecture of this system is at once familiar in its broad outlines and strange in its specifics, with rocky inner worlds and outer gas giants arranged in a sequence that rhymes with, though does not quite echo, the solar system's own structure. It stands as a beautiful example of how the same broad theme of planetary formation can produce endlessly different variations. One of the most robust statistical patterns in exoplanet science is the observation that gas giant planets are more commonly found around stars with higher metallicity, a term astronomers use for the proportion of elements heavier than hydrogen and helium present in a star's atmosphere. Stars with metallicity similar to or above that of our Sun are roughly 3 times more likely to host a detectable giant planet, because a metal-rich disk contains more solid material to build the rocky cores that must form first before a gas giant can begin accreting its gaseous envelope. Our own sun's metallicity is comparable to or slightly above the average for nearby stars of its age, a characteristic that is entirely consistent with it having produced a system including a gas giant like Jupiter, and which, in a small way, links the chemistry of our own planetary system to the broader patterns of the galaxy. If we could observe exoplanets from up close and look at them as whole disks of color, many of them would present hues quite unlike Earth's familiar blue and white. HD 189733b would appear a deep, saturated cobalt blue, its color produced by silicate haze rather than oceans. A hot Jupiter with iron-rich clouds might appear dark reddish-brown or nearly black. A water world with a thick steam atmosphere might shimmer in pale gray and soft white, like a pearl seen from a distance. And a planet orbiting a red dwarf would receive so much of its light in deep red and infrared wavelengths that even an Earth-like atmosphere would scatter those wavelengths differently, producing a sky and a planetary surface that glows in salmon pinks and deep amber rather than the blue that has defined our view of habitability from the beginning. Just as planets in our solar system are orbited by moons, many exoplanets are expected to host moons of their own, objects called exomoons, whose detection would add an entirely new dimension to our understanding of planetary systems. Detecting an exomoon is significantly harder than detecting an exoplanet, because a moon produces an even smaller perturbation in the light curves astronomers analyze. The most compelling exomoon candidate discovered so far orbits the gas giant Kepler 1625b and appears to be roughly Neptune-sized, a moon of extraordinary proportions that, if confirmed, would be unlike anything in our solar system. A confirmed exomoon detection remains one of the most anticipated milestones in the field, because large, complex moons orbiting gas giants in habitable zones could themselves be temperate rocky worlds with liquid water and stable temperatures. Most planets orbit their stars in the same direction that the star rotates, a shared directionality that reflects the original rotation of the disk from which both were born. WASP-17b, discovered in 2009, was the first confirmed exoplanet found to orbit in the retrograde direction, moving counter to its star's spin in a configuration that could not have arisen from simple disk formation and must instead reflect a dynamic history of gravitational interactions that flipped the planet's orbit entirely. Its existence provides important evidence for the theory of high eccentricity migration, in which gas giants form far from their stars and are gradually deflected into close, hot orbits through gravitational encounters, a process that can produce retrograde orientations as a natural byproduct. Backward orbiting planets are a gentle reminder that planetary systems are not born serene, but are shaped by billions of years of invisible gravitational forces working quietly in the dark. Tidal heating is a process in which the gravitational stretching and squeezing of a planet or moon by a nearby massive body converts mechanical energy into heat within its interior, most dramatically illustrated in our solar system by Io, Jupiter's innermost large moon, whose continuous tidal flexing drives the most intense volcanic activity of any body in the known solar system. Applied to exoplanets, tidal heating becomes an additional internal energy source for rocky worlds in tight orbits around their stars, or for moons orbiting massive exoplanets, potentially keeping such worlds geologically active and even maintaining subsurface liquid water regardless of their distance from starlight. The concept of tidal heating as a source of warmth entirely independent of a star expands the inventory of places where liquid water, and potentially life, might exist to include worlds far beyond any star's habitable zone. Gravitational microlensing is a planet detection technique that exploits Einstein's prediction that massive objects bend and magnify the light of more distant background sources, acting as natural cosmic lenses that can temporarily amplify a background star's brightness when a foreground star and its planets align closely as seen from Earth. When a background star aligns with a foreground planetary system, the planet adds a brief, distinctive spike to the brightening event, a spike that can be precisely modeled to infer the planet's mass and orbital distance. Microlensing is particularly powerful for finding planets at intermediate orbital distances around very distant stars in the galactic bulge, detecting worlds in a region of parameter space that the transit and radial velocity methods largely cannot access, and each lensing event is a singular, transient observation that will never repeat. A planet glimpsed once in a cosmic spotlight before the alignment shifts and the moment is gone. The young star PDS-70, approximately 5 million years old and located about 370 light-years away, hosts two directly imaged planets, PDS-70b and PDS-70c, that are still actively accreting gas from the surrounding protoplanetary disk, surrounded by circumplanetary material that may be in the process of forming moons in real time. The detection of these worlds required sophisticated instruments capable of distinguishing planet signal from disk signal, but the resulting images, showing two luminous young planets still glowing with the heat of their accretion, are among the most scientifically extraordinary exoplanet images ever obtained. Studying these young forming worlds is, in many ways, the study of our own solar system's ancient past, a glimpse backward 4.5 billion years to when our own planets were young, hot, and still drawing in the raw material of their formation. Astrobiologists have proposed that the best worlds for life might not be Earth-like worlds at all, but rather larger, warmer, older, and wetter, what researchers have termed superhabitable worlds, whose properties might make them even more conducive to the origin and flourishing of life than Earth itself. A superhabitable world might be approximately 1.5 times Earth's mass, slightly warmer on average, with more ocean coverage, and orbiting a slightly cooler and longer-lived orange dwarf star that could provide stable illumination for 12 to 15 billion years rather than the Sun's 10 billion-year lifespan. The concept is speculative by necessity, since we have only one confirmed example of a life-bearing world, but it serves the important purpose of reminding us that Earth, wonderful as it is, need not be the best possible world that the universe can produce, only the best one we happen to know about. The first genuine direct image of an exoplanet, a photograph in the truest sense, was obtained in 2004 by astronomers using the European Southern Observatory's Very Large Telescope in Chile. The planet, called 2M1207b, orbited not a main sequence star but a brown dwarf about 170 light-years away, and the image showed both objects as separate, distinct points of infrared light. Modest as it appeared, two faint dots on a detector, its significance was enormous. For the first time in human history, the light of a planet orbiting another star was not inferred from its gravitational influence or its shadow across starlight, but was genuinely, directly received, collected by a telescope, and recorded in a file on a computer in a building in the Chilean desert. A photograph, however small, is a different kind of knowing. The history of exoplanet discovery follows one of the most dramatic exponential growth curves in the history of science, from a handful of tentative detections before 1990, to the first confirmed planet around a Sun-like star in 1995, to the gradual acceleration of the early 2000s, to the transformative flood released by the Kepler telescope from 2009 onward. The 1,000th confirmed exoplanet was announced in 2013, the 3,000th in 2016, the 5,000th in 2022, each milestone passed with increasing speed. The current rate stands at hundreds of confirmed discoveries per year, driven by the TESS mission's continuous all-sky survey and ongoing analysis of Kepler's rich archival data, and future missions are expected to push the total well beyond 10,000 confirmed worlds within the next decade, a number that was unimaginable at the dawn of the field. A biosignature is a chemical or physical feature of a planet that can only be produced, or is most plausibly explained, by the presence of living organisms, and the search for biosignatures in exoplanet atmospheres is one of the most scientifically ambitious and philosophically profound endeavors in the history of human inquiry. The most widely discussed atmospheric biosignature is molecular oxygen, because on Earth it is produced almost entirely by photosynthetic organisms and would be rapidly consumed by geological processes in their absence. Scientists prefer to look for combinations of gases, such as oxygen paired with methane, or ozone alongside a reducing gas, that would be chemically incompatible in the long term without a continuous biological source to maintain them simultaneously. That combination, if detected, would be perhaps the most significant scientific discovery in human history. One of the most quietly profound aspects of observing exoplanets is that the light we use to study them is not present-moment light but ancient light. Photons that left their source years, decades, centuries, or millennia ago and have been traveling at 300,000 kilometers per second ever since. The TRAPPIST-1 system, 40 light-years away, is being studied using light that left it approximately 40 years ago, when personal computers were new inventions and no one had yet confirmed the existence of any exoplanet. An exoplanet 1,400 light-years away, like Kepler 452b, shows us its properties as they were in the year 620, and this means that we are not, in a strict sense, astronomers of the present universe, but careful historians of an ancient one, reading letters written long before we existed and only now receiving them in our patient instruments. Star clusters, gravitationally bound groups of stars born from the same gas cloud and orbiting together through the galaxy, were long thought to be poor hosts for stable planetary systems, because the frequent close stellar encounters in such dense environments might gravitationally disrupt orbits before planets had time to form or settle. However, observations have revealed planetary systems in several open clusters, including at least 2 confirmed planets orbiting stars in the Hyades cluster, the nearest star cluster to Earth, about 150 light-years away, demonstrating that planets can form and survive even in the relatively crowded stellar environments of young open clusters. Finding planets in star clusters allows astronomers to study planetary systems around stars whose ages are known with unusual precision, since all stars in a cluster are born at approximately the same time from the same initial cloud of material. Planets form within protoplanetary disks, flattened, rotating structures of gas and dust surrounding newly formed stars in the first few million years of their existence, and the process by which specks of dust ultimately become rocky planets and gas giants spans a rich chain of physical processes playing out over millions of years. The Atacama Large Millimeter Array in Chile has imaged the internal structure of dozens of these disks in extraordinary detail, revealing concentric rings, gaps, and spirals in the dust distribution that are widely interpreted as the gravitational footprints of young planets carving clear paths through the disk material as they orbit. These images are, in a very real sense, photographs of solar systems in the process of being assembled, the earliest possible chapter of a story that, billions of years later, might include oceans, continents, and perhaps something that looks up at the sky and wonders. The Kepler-11 system, located approximately 2,000 light-years from Earth, was announced in 2011 as one of the most densely packed planetary systems ever discovered, containing 6 planets orbiting a Sun-like star, 5 of them packed into orbits smaller than the orbit of Mercury around our Sun. All 6 planets fall into the super-Earth and sub-Neptune size categories, and the gravitational interactions between the innermost 5 are strong enough to produce measurable variations in their transit timings that allow their masses to be calculated with impressive precision. The existence of a 6-planet system this compact, stable for billions of years despite its crowded orbits, demonstrates that the universe can produce planetary families far more tightly woven than our own, fitting multiple worlds into the space where our solar system left only empty distance. Ultra-hot Jupiters, hot Jupiters receiving particularly intense stellar radiation, lose their atmospheric gas at rates that, over geological timescales, can dramatically reduce their mass and alter their fundamental nature. Some of these worlds are observed to have comet-like tails of escaping gas streaming away from them as they orbit, their atmospheres being slowly but continuously peeled away by the energy of the star they are so close to. The ultimate fate of a gas giant that loses enough atmosphere in this way is thought to be a so-called Thonian world, a dense, rocky or metallic remnant core from which all the lighter elements have been stripped. A world that began its existence as something like Jupiter and ends it as something dense and bare and ancient, a geological core exposed to the starlight after billions of years of slow, quiet loss. The habitable zone is not a fixed set of distances but shifts considerably depending on the brightness and type of the host star, ranging from very close in around faint red dwarfs to very far out around bright blue or white giants. Red dwarf stars, the most common and longest-lived type in the galaxy, comprising about 70% of all stars, have habitable zones at orbital distances of only a few hundredths to a few tenths of an astronomical unit, so close that tidal locking, stellar flares, and intense stellar winds become important factors in whether a planet there could sustain liquid water and stable chemistry. The debate over whether red dwarf habitable zones are genuinely hospitable balances the long-term stability and extraordinary longevity of these dim stars against the challenges their activity levels pose for planetary atmospheres, and it remains one of the most active and consequential debates in contemporary astrobiology. On Earth, seasons arise from the gentle 23.5-degree tilt of our axis, a mild inclination producing the familiar cycle of spring, summer, autumn, and winter. On exoplanets, seasonal variation can reach extremes that make Earth's seasons feel almost imperceptible by comparison. A planet with an axial tilt approaching 90 degrees, tilted nearly on its side like Uranus, would experience seasons where each pole spends an entire year in uninterrupted sunlight followed by an entire year in total darkness, a rhythm of such extremity that the biological concept of a comfortable seasonal cycle would need to be entirely reconceived. A highly eccentric orbiting planet, like HD 80606b, would experience temperature swings of hundreds of degrees over the course of a single year, driven not by axial tilt but by the dramatic variation in its distance from its star. Planetary migration refers to the change of a planet's orbital distance from its star over time, driven by gravitational interactions with the gas and dust of the protoplanetary disk or by exchanges of energy with other planets in the system. In our solar system, the Grand Tack hypothesis proposes that Jupiter migrated inward toward the Sun early in its history before being pulled back outward by Saturn's gravitational influence. a journey that may have been decisive in shaping the architecture of the inner solar system, including the relatively small size of Mars and the particular distribution of the asteroid belt. The hot Jupiters observed around distant stars are the most dramatic evidence for migration in exoplanetary systems, representing gas giants that formed far from their stars and traveled inward over millions of years to their current scorching close-in orbits, a journey encoded in their present position. The color of a planet's sky depends on what its atmosphere is made of and what wavelengths of light its star primarily emits, and across the diverse population of exoplanets, sky colors would range from the deep red of a world orbiting a red dwarf, through the pale yellow cream of a thick carbon dioxide atmosphere, to the dark navy of a thin, dry atmosphere that scatters almost no light at all. On a tidally locked planet, the dayside sky might be a perpetual blazing white or pale gold, while the nightside sky would be a perfect, unbroken black filled from horizon to horizon with unmoving stars. The variety of possible sky colors across the galaxy, colors that no human eye has ever seen, is one of the quietest and most beautiful expressions of the diversity that the universe has assembled in the billions of years since the first stars began to shine. Earth's magnetic field, generated by the circulation of molten iron in the outer core, serves as a protective shield deflecting the energetic charged particles of the solar wind away from the atmosphere, helping to preserve the stable surface conditions that life depends upon. Detecting magnetic fields around exoplanets is extraordinarily difficult with current instruments. But the question of whether a potentially habitable exoplanet has a magnetic field is one of the most important factors in assessing its long-term habitability, particularly for rocky worlds orbiting active red dwarf stars that produce intense stellar winds and energetic flares. Future radio telescope arrays and dedicated space missions are expected to eventually map the magnetic environments of nearby exoplanets systematically, adding another essential layer to the growing portrait of what makes a world capable of sustaining complex chemistry over geological time. The NASA Exoplanet Archive, maintained by the California Institute of Technology under a NASA contract, is the definitive public database of all confirmed exoplanets and their measured properties, the single authoritative reference that astronomers, students, and the general public can consult to find up-to-date information on every world confirmed to exist beyond our solar system. The archive contains data for more than 5,500 confirmed exoplanets, standardized from dozens of different discovery teams and instruments into a uniform format that allows comparison and statistical analysis across the entire known planetary population. It is freely accessible to anyone with an internet connection, a publicly funded, publicly available record of one of the most significant expansions of human knowledge in history, open to any curious mind anywhere on Earth. The aerial mission, approved by the European Space Agency and planned for launch in 2029, is the first space telescope specifically and exclusively designed to study the atmospheres of exoplanets in a systematic survey-based manner. Not as individual targets of opportunity, but as a comprehensive, deliberate population study. Aerial plans to observe approximately 1,000 exoplanets over a 4-year primary mission, measuring atmospheric compositions, temperatures, and cloud properties across the full range of planetary types from hot Jupiters to rocky super-Earths. The mission represents a maturation of exoplanet science from the era of discovery into the era of systematic characterization, a shift from asking which worlds exist to asking, with patience and rigor, what each of them is actually like. The discovery of exoplanets in their thousands has changed humanity's understanding of its place in the universe in a way that the Copernican revolution, which moved Earth from the center of the cosmos to one planet among several, did not quite complete. We now know that we live on one planet among hundreds of billions in our galaxy alone, that rocky worlds in habitable zones are common, and that the conditions broadly associated with life are not exceptional or rare in the universe's raw inventory. What remains unknown, and what makes each day of continued exoplanet science genuinely significant, is whether any of these worlds has crossed the particular threshold from chemistry to biology, from complexity to life, from matter to the capacity to wonder. Every new world added to the catalogue is not merely data, but a new candidate, a new possibility, a new quiet question waiting in the dark. The Planet Hunters project, run through the Zooniverse Citizen Science platform, enlisted hundreds of thousands of volunteers to visually examine light curves from the Kepler mission's archive, leading to the identification of unusual signals that professional automated pipelines had missed, including the famous Boyajian star, whose irregular, dramatic dimming sparked years of scientific investigation. Several exoplanet candidates have been flagged first by citizen scientist volunteers and only subsequently confirmed by professional follow-up observations, making the amateur community a genuine contributor to the exoplanet census. This democratization of exoplanet science, the ability of anyone with an internet connection to participate in analyzing real data from space telescopes, represents a genuinely new kind of scientific collaboration. One in which the universe's invitation to be explored is extended not only to professional astronomers but to anyone who finds the night sky worth paying attention to. Artificial intelligence and machine learning have become indispensable tools in modern exoplanet science, helping astronomers extract planetary signals from enormous datasets that would take human analysts years to examine individually. A deep learning neural network developed by Google, applied to Kepler data in 2017, identified two previously overlooked exoplanets, including one in the Kepler 90 system that brought that system's total to 8 confirmed planets, tying our solar system's count for the first time. Machine learning classifiers now routinely process test light curves in near real time, separating genuine planetary transit signals from the false positives produced by eclipsing binary stars and instrumental artifacts. The collaboration between human curiosity and machine pattern recognition has become one of the defining features of 21st century astronomy, a partnership that is expected to grow more central to the field with each new generation of sky surveys. Somewhere in the galaxy, statistically likely within a few hundred light-years of Earth, perhaps within just tens of light-years, there is almost certainly a rocky planet of roughly Earth size orbiting a sun-like or orange dwarf star at the right distance for liquid water. With an atmosphere, with geology, with the slow carbon cycling that helps planets maintain stable climates over billions of years. We have not found it yet, not because it does not exist, but because we do not yet have the instruments to detect it conclusively. The search for this world is not a romantic metaphor but a literal scientific program, with specific targets, specific instruments under construction, and specific measurable criteria for success. Whether that success arrives in 10 years or 50, its eventual arrival seems increasingly like a question not of possibility but of patience. Of continuing to build the tools, train the scientists, and ask, with everything we have, whether the light of distant suns falls on anyone else's shore. Globular clusters are dense, spherical congregations of hundreds of thousands to millions of stars, gravitationally bound together and orbiting the centers of galaxies in vast halos. And for many years astronomers wondered whether the crowded stellar environments of these ancient clusters could support stable planetary systems given the frequency of close stellar encounters that might gravitationally disrupt orbits. The question was addressed observationally when the Hubble Space Telescope conducted a transit survey of the globular cluster 47 Tucani in 2000. Searching for hot Jupiters transiting its stars, and found none, despite expecting to detect many if hot Jupiter frequencies were similar to those around field stars. This deficit was tentatively interpreted as evidence that the very low metallicity of globular cluster stars. They contain far fewer heavy elements than younger stars like our Sun, might reduce the efficiency of planet formation, since rocky planets and the solid cores of gas giants are built from heavy elements. However, subsequent work and discoveries have complicated the picture, with candidate exoplanet detections in other globular cluster stars and theoretical arguments suggesting that stable planetary orbits can persist in globular clusters under many conditions. The first confirmed exoplanet in a globular cluster remains an important goal for astronomical surveys, because such a world would orbit a star formed in one of the oldest stellar populations in the universe, potentially offering a window into planetary systems from the earliest chapters of galactic history. Volcanic activity is one of the most fundamental geological processes on rocky planets, driven by the decay of radioactive elements in the interior and by the residual heat of planetary accretion, and it plays crucial roles in shaping a planet's surface, releasing gases into its atmosphere, and cycling elements between the deep interior and the surface environment. On Earth, volcanism has been a primary driver of atmospheric composition throughout history, releasing water vapor, carbon dioxide, and sulfur gases that have interacted with the surface and ocean chemistry over billions of years. On rocky exoplanets, especially those with higher masses, tighter orbits, or active tidal heating, volcanism might be far more intense and sustained than anything Earth has experienced since its earliest, most violent geological era, potentially covering the surface in fresh lava flows, filling the atmosphere with volcanic gases, and driving rapid atmospheric evolution. Io, the most volcanically active world in our solar system, provides a nearby example of extreme tidal volcanism, but ExoIOS orbiting more massive gas giant exoplanets might make even Io seem modest by comparison. Whether intense volcanism makes a rocky world more or less habitable is genuinely uncertain. It is destructive in excess, but it also releases gases that can sustain an atmosphere, drives hydrothermal vent systems that may support life, and contributes to the long-term geochemical cycles that regulate a planet's climate. Carl Sagan's famous description of Earth as a pale blue, inspired by the 1990 photograph of Earth taken by Voyager 1 from a distance of 6 billion kilometers as the spacecraft was leaving the solar system, remains one of the most philosophically resonant moments in the history of space exploration, and the study of exoplanets has deepened that perspective in ways that even Sagan, who died in 1996, only partially lived to imagine. Every exoplanet we discover is, in a sense, someone else's pale blue, a world that, if inhabited, would appear from sufficient distance as nothing more than a tiny point of light lost in the glare of its parent star, yet might be home to oceans, mountains, weather, and whatever forms of complexity the chemistry and physics of that particular world have been able to assemble over the billions of years of its existence. The Earth is not special by virtue of being the only rocky world in a habitable zone. The universe, as we have seen, provides those in numbers beyond reckoning. But it may be special in the ways it has unfolded, in the particular history of its geology, its oceans, its carbon chemistry, and the unlikely series of evolutionary steps that eventually led to organisms capable of looking outward and asking what other pale dots there might be. Exoplanet science is, in its deepest sense, the systematic extension of Sagan's original meditation. The slow, painstaking accumulation of evidence about how many dots there are, how varied they are, and whether any of them are, in some meaningful sense, someone else's home. The chemical composition of an exoplanet, the specific blend of elements and compounds that make up its bulk, is determined by the composition of the protoplanetary disk from which it formed, which is in turn inherited from the molecular cloud that gave birth to the host star, and which reflects the nucleosynthetic history of that region of the galaxy over billions of years of stellar births, lives, and deaths before the current system formed. Stars that are rich in carbon relative to oxygen are expected to produce planetary systems with different bulk compositions than oxygen-rich stars like our Sun, potentially forming planets where carbides replace silicates as the dominant mineral class, carbon planets whose mantles of silicon carbide and graphite, rather than rock, would make them chemically alien by every terrestrial standard. Iron-poor stars would form iron-poor planets with smaller cores, while alpha-element-rich stars might produce planets with higher proportions of magnesium and calcium silicates. These compositional variations propagate through every aspect of a planet's structure and geological behavior, from the size and activity of its core to the chemistry of its volcanic gases to the minerals available at its surface for whatever chemistry might take place there. The universe's planets are not all made of the same stuff, any more than the universe's stars are, and the chemical diversity of exoplanets, still largely unexplored, may prove to be as vast as any of the other dimensions of planetary diversity that exoplanet science has already revealed. The Fermi paradox, named for physicist Enrico Fermi's informal 1950 question about why, given the vast age and size of the universe and the apparent abundance of potentially habitable worlds, humanity has not yet detected any signs of extraterrestrial intelligence, takes on additional weight and texture with every new exoplanet discovery that confirms the universe is rich in rocky worlds, many of them in habitable zones, some of them billions of years older than Earth and therefore with far more time for any emerging intelligence to have spread across the galaxy. The various proposed resolutions of the Fermi paradox fall broadly into two categories. Those that argue intelligence is extraordinarily rare despite the abundance of habitable worlds, suggesting that one or more steps in the path from simple chemistry to technological civilization are so improbable that they have occurred only once or a handful of times in the observable universe. And those that argue technological civilizations are common but that some factor distance, the difficulty of communication, the short lifetime of civilizations, or deliberate silence explains the absence of detected signals. Every confirmed Earth-sized planet in a habitable zone sharpens the paradox rather than resolving it, because it rules out planetary rarity as the explanation for the silence. If the universe provides the real estate in such abundance, the explanation for the quiet must lie elsewhere. The exoplanet census is, in this sense, one of the most important inputs to one of the oldest and most profound questions humanity has ever asked, not by providing the answer, but by steadily eliminating the simplest and most comfortable non-answers. The habitable zone is not a fixed set of distances but shifts dramatically depending on the type and luminosity of the star at the center of the system, which means that a planet sitting at exactly 1 astronomical unit from its star might be perfectly temperate around a Sun-like star, but roasting in an inferno around a more luminous star and frozen solid around a dimmer one. Around the most luminous blue giant stars, the habitable zone lies at distances of tens or hundreds of astronomical units farther out than the outermost planets in our own solar system, and these massive, short-lived stars burn through their hydrogen fuel so quickly that they may not provide stable illumination long enough for complex life to develop. Red dwarf stars, the most common and long-lived stars in the galaxy, have habitable zones that lie very close in at distances of only a few hundredths to a few tenths of an astronomical unit. And because red dwarfs burn so slowly, they will remain stable for tens to hundreds of billions of years, providing an extraordinarily long window of potential habitability for any worlds they host, far longer than our own sun will shine. The relative merits of different star types as potential hosts for life are the subject of considerable scientific debate, balancing the tidal locking and flare activity problems of red dwarf habitable zones against the stability and longevity advantages that make them, in the long run, the most durable platforms for life that the universe provides. The universe's stellar population, taken as a whole, provides a vast variety of habitable zone architectures, each with its own combination of challenges and opportunities for whatever chemistry might find them. The fundamental challenge of exoplanet observation is one of contrast and distance. A planet is an object that produces no light of its own beyond the faint thermal glow of its own heat, reflecting only a small fraction of the light from its star. And yet it orbits that star at such a small angular separation as seen from Earth that distinguishing its signal from the overwhelming glare of the star requires techniques of extraordinary ingenuity and precision. For a Jupiter-sized planet reflecting light from a Sun-like star at a typical exoplanet distance, the contrast ratio between star and planet is roughly 1 billion to 1 in visible light, meaning that the planet contributes only 1/billionth of the combined system's brightness, a ratio that makes detecting the reflected light directly roughly equivalent to searching for a firefly hovering beside a lighthouse from across the Atlantic Ocean. Even the transit method, which is far more sensitive than direct reflection detection, requires measuring changes in stellar brightness of the order of 1 part in 10,000 for a Jupiter-sized planet, and 1 part in 10 million for an Earth-sized planet, a level of photometric precision that was considered near impossible before space-based missions eliminated the blurring effects of Earth's atmosphere. The solutions to these challenges: star shades, coronagraphs, interferometry, adaptive optics, phase masks, and dozens of other technical innovations, represent some of the most creative engineering in modern astronomy, each one a different way of answering the same simple question: how do you find a mote of dust beside a lighthouse in the dark? Astrobiology, the scientific study of the origin, evolution, distribution, and future of life in the universe, has been transformed by the exoplanet revolution from a field with a single data point, Earth, to one with a growing population of objects to study and compare, even if none of those objects has yet yielded direct evidence of life. The field sits at the intersection of astronomy, biology, chemistry, geology, and planetary science, asking questions that no single discipline can answer alone. What physical and chemical conditions are necessary for life to arise? What minimum requirements must a planet meet to sustain it? And what signatures would life leave on a planet's atmosphere, surface, or orbit that could be detected across the vast distance that separates us from other worlds? One of astrobiology's central findings is that life on Earth is far more robust and adaptable than once thought, thriving in environments previously considered uninhabitable. Deep-sea hydrothermal vents in total darkness and crushing pressure, acidic hot springs, frozen tundra, and the deep crust of the Earth kilometers below the surface. suggesting that the envelope of conditions under which life can exist is considerably wider than Earth's comfortable surface biosphere might imply. This robustness, combined with the abundance of potentially habitable environments revealed by the exoplanet census, has made astrobiologists increasingly confident that if life arose on Earth, it is likely to have arisen elsewhere as well, though the nature and complexity of any such life remains entirely open. Astrobiology is, in its essence, the attempt to answer the question that every human being has wondered about at some point while looking at a sky full of stars. At the upper end of the mass spectrum for confirmed exoplanets, beyond which objects transition into the brown dwarf category and eventually to stellar companions, sit the superjupiters, planets with masses ranging from several times Jupiter's mass up to approximately 13 Jupiter masses. Beyond which deuterium fusion would technically make them brown dwarfs by the most widely used definition. Several confirmed exoplanets sit near this upper boundary, their mass estimates carrying enough uncertainty that their classification as planet or brown dwarf remains technically ambiguous, and the scientific community has not entirely standardized the criteria for drawing the line. HAT P2b, with a mass approximately 9 times that of Jupiter, is one of the most massive clearly planetary classified exoplanets, orbiting a slightly more massive star than our Sun on a moderately eccentric orbit. Kappa Andromedae b, a directly imaged companion approximately 13 Jupiter masses orbiting a blue-white star about 170 light-years away, sits exactly at the conventional planet-brown dwarf boundary and has been claimed as both depending on which definition is applied. The existence of these borderline objects is scientifically productive precisely because it forces precise thinking about what makes a planet, a question that turns out to be less about a single number and more about the history, context, and formation pathway of the object in question. A judgment that the universe has not made easier by providing a clean and obvious dividing line. There is a category of exoplanets sometimes called ultra-hot Jupiters whose dayside temperatures are so extreme, exceeding 2000 degrees Celsius in many cases, with some surpassing even 3000 degrees, that their atmospheric chemistry undergoes a dramatic and bizarre phase transition. At these temperatures, the water molecules, carbon monoxide, and other compounds that make up the atmospheres of cooler hot Jupiters are broken apart into their atomic components, and even molecular hydrogen dissociates into its constituent atoms. This atomic atmosphere on the day side then recombines into molecules on the cooler night side, and the energy released by this recombination provides an additional mechanism for heat redistribution around the planet that goes well beyond simple wind transport. KELT 9b holds the record as the hottest known exoplanet, with a dayside temperature of approximately 4,300 degrees Celsius, hotter than many types of stars, orbiting an extremely luminous blue-white star at an orbital distance that makes Mercury's proximity to our Sun seem leisurely. At these temperatures, even the night side of KLT 9b exceeds 2000 degrees, and the planet is slowly losing mass to a comet-like tail of evaporating atmospheric material streaming away from the intense stellar heating it receives. KELT 9b is, in the most literal sense, a world caught between the conditions of a planet and the conditions of a star, occupying an extreme corner of parameter space that challenges every existing model of atmospheric physics and reminds astronomers that the universe is, in practice, more extreme than theory tends to prepare us for. While many exoplanetary systems discovered so far differ dramatically from our own solar system's architecture, with hot Jupiters hugging their stars and compact systems of sub-Neptunes packed within Mercury's orbital distance. A growing number of systems have been found whose broad features bear a meaningful resemblance to our own, hosting multiple rocky inner planets and more distant gas giants in arrangements that, if not identical to our solar system, at least suggest that solar system-like architectures are possible, repeatable, and perhaps even common. While many exoplanetary systems discovered so far differ dramatically from our own solar system's architecture, with hot Jupiters hugging their stars and compact systems of sub-Neptunes packed within Mercury's orbital distance. A growing number of systems have been found whose broad features bear a meaningful resemblance to our own, hosting multiple rocky inner planets and more distant gas giants in arrangements that, if not identical to our solar system, at least suggest that solar system-like architectures are possible, repeatable, and perhaps even common. Kepler 90, located approximately 2,500 light-years away, hosts 8 confirmed planets, tying our solar system for the most planets known around a single star at the time of its discovery, arranged from very small and rocky in the inner orbits to larger and gassier in the outer orbits, a general pattern that our own solar system also follows. The system Epsilon Eridani, one of the nearest Sun-like stars at approximately 10 light-years distance, shows evidence for both an inner and an outer debris disk analogous to our asteroid belt and Kuiper belt, suggesting a structural similarity to our solar system's architecture at the large scale. Finding solar system analogues is scientifically important because it tests theories of planet formation that were largely developed on the basis of our own solar system, and every analog found either validates or challenges those theories in ways that pure modeling cannot. Our solar system may not be typical, but the growing catalogue of systems with familiar features suggests that it is not entirely unique either, that the universe has found this particular arrangement of worlds at least more than once. One of the most quiet and profound aspects of observing exoplanets is that the light we use to study them, whether we are measuring a transit, analyzing a spectrum, or capturing a direct image, is not present-moment light but ancient light, light that left its source years, decades, centuries, or millennia ago and has been traveling at 300,000 kilometers per second ever since, carrying within it a frozen record of the exoplanet's state at the moment the light departed. An exoplanet 100 light-years away, studied by a transit observation today, is showing us its properties as they were 100 years ago, during a year on Earth when the First World War was being fought and no one on this planet had yet seen a confirmed exoplanet, had yet imagined the specific world we are looking at. An exoplanet in the Andromeda Galaxy, if we could observe its transits, which we cannot, yet, would be showing us a world as it was 2.5 million years ago, before our own species had yet evolved. The light from TRAPPIST-1 and its planets left that system approximately 40 years ago, when the personal computer was a new invention and the concept of atmospheric spectroscopy of exoplanets was science fiction. We are, in this sense, not astronomers of the present universe but historians of an ancient one, reading letters whose postmarks predate our ability to read, whose senders could not have known they were writing to us and whose contents we are only now, with patient and extraordinary instruments, beginning to decipher. The Kepler 11 system, located approximately 2,000 light-years from Earth in the constellation Cygnus, was announced in 2011 and immediately captured widespread attention because it contains 6 planets orbiting a Sun-like star, 5 of which are packed into orbits smaller than Mercury's orbit around our Sun. A level of orbital compactness that was unprecedented at the time and that provided extraordinary insights into the range of possible planetary system architectures. All 6 planets are between 2 and 13.5 times the mass of Earth, placing them in the super-Earth and sub-Neptune categories, and all of them orbit their star within about half an astronomical unit, closer than Venus is to our Sun. The gravitational interactions between the 5 innermost planets are strong enough to produce measurable transit timing variations, slight changes in the exact timing of each planet's transit caused by the mutual gravitational tugs between them, allowing astronomers to measure the planet's masses without radial velocity observations. The densities of the 5 inner planets were found to be lower than Earth's density, suggesting they retain significant amounts of gas or water in their composition rather than being purely rocky worlds. The Kepler-11 system is, in a sense, a demonstration that the universe is capable of arrangements far more densely packed than our own solar system, fitting multiple planets where our solar system has left vast empty space, and doing so in configurations that prove to be gravitationally stable over billions of years.